Hello, 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 hello. We are live. This is not a test. This is not a drill. We are indeed live, and we're very happy to hopefully see many of you today. Sorry that I wasn't live for a couple of nights. I was taking a little break, had some other things to accomplish, and I am so very happy that we are here today. Baji is on the sofa with me tonight, and we will talk about the early universe, the very hot, dense, exciting, lots of interactions taking place type of early universe from the book A Brief History of Time by Stephen Hawking. We have been kind of going back and forth between this book and Brian Greene's The Elegant Universe, but today we will talk about A Brief History of Time once again, the origin. See, let me tell you about the chapter we're on. This is called The Origin and the Fate of the Universe, and we're at the section known as well, there's a bunch of questions actually that we are going to take a look at and then start to address in this particular chapter. So once again, welcome one and welcome all. So very excited that many of you might be showing up and hopefully saying hi to us soon here. If you're here, do say hello in the chat, and I will read your comments. I will chit chat and update anybody with what's going on. And it is the time to party. So hello. Hello, Nathan. Hello, Doro. So Nathan, hello, hello, hello. Nathan says hello, B. Time to party, says Doro. So yes, indeed, it is the time to party. Indeed it is. It is here. The time to party is here. We will do a little bit of learning and things like that. She won't chit chat. It'll be 5-hour water breaks. Let's get 20 likes. That's very true. Let's get 20 likes with all these periods in between. I will pin that message. Thank you so much, Dora Madness. Thank you so much, Nathan, as always, for being here. I do hope that we will see many more of our friends here tonight, old and new. And indeed, we will, well, we can chit chat at first, and while we wait for some more people to join. And in fact, I should share the live. But if there is some particular chit chatting that you want to do, that you want me to read, go ahead, say it in the comments, and then I will get started with the topic of today. So once again, thank you so much. Thank you, one, and thank you all. Welcome, welcome, welcome. Welcome, welcome, welcome. I am indeed wearing some lipstick again. This is a Lakme, some kind of lipstick that I got as a gift, and these are some earrings as well. Actually, these earrings have a story there from West Virginia. So, just so you know, when I was up in the mountains at one time, a long time ago, once upon a time, I bought these earrings. We will have Harper and Chickpea break in here. Everyone will be banned. It will be a good time, 10 on 10. Exactly. Thank you so much, Doro, for kind of putting forth what is about to happen here. I think Doro is joking, but not really. It's that type of thing where it's sort of a half-truth, sort of could just happen that way. Who knows? If Harper joins, I will tell people, I will warn you that we have a very strict mod if they join. Stitch High says hi. Hello, Stitch High. Hello, Professor. It's time to party, says Professor Nick. Faye says, hey. Nathan says, as usual, it is my bedtime, so if I fail to respond, I'm sleeping to your peaceful reading. Of course, feel free. Nathan, you should feel free to start to close your eyes and just kind of enjoy the peaceful reading in the background here. I will try to do my ASMR peaceful reading mode as much as I can. Once I as much as I can remember. If I forget to ASMR, that's because I've just forgotten. But I will try to whisper sometimes. Professor says, Doro, how are you even here? Go to bed. Nathan is sleepy. Very nice. Thank you so much, guys. We will get started with the topic in just 1 second. Let me share the live. And if you could share the live, if you could like the live, subscribe, share, all that stuff, comment, that would be most amazing. If you want to give us a super chat, again, most amazing, and already thankful for that. So can we get 10 likes? Can we get 20 likes? Could we get 10 likes? If there's 11 people here, could we please get 10 likes? That would be most amazing in my mathematics. If we could get some sleep. Oh gosh. I'm reading the chat as I speak, and so my words are getting a little bit jumbled up. So Dora says hashtag never sleep. And I was trying to say that can we get some likes? And we will start with our topic here. So where is my live? How do I share it? Thank you everybody for being here. Do you even know English? That's exactly right. You know, sometimes I do wonder, do people really know English or not? At the rate at which sometimes people will be acting, I'm really unsure. I'm really quite unsure. And where is this Reese? You know, ever since he found out that he will be having a child, he has been pretty much ignoring the lives and not coming here to do his mod duties. So Reese, miss you and hope everything is good. And if you could please like and share and subscribe, and ask your family members to like and share and subscribe, and your new child to like and share and subscribe, that would be most amazing. And can you please like the live? Thank you so much. I miss Reese. He's the real mod of this channel. Aw, he did become a mod a while ago. I think it was before your time, Doro. I forget, but yes, indeed he did become a mod and all that stuff. But where is he now? He is having babies. So, you know, such is life. Keeps going. Uh, People are being born and I just keep on going live, you know. That's just what I do. So, congratulations. Congratulations to everybody who's having a child. I do hope that the children will subscribe as well. And we will continue to continue. We will continue to continue these topics in physics, cosmology, astrophysics, astronomy, along with Baji, Fuji, and Suji, my children who are cats that I've birthed. He's the real mod. Me, Ver, and Harper are pretenders. Well, Harper takes the job very seriously indeed when he or she makes it here. He or she or they makes it to the live. They take the job very seriously indeed. And Dora, always good to have you. I'd have kids just to yell at them. Oh my gosh, well, Professor Mick, that is quite horrifying. Horrifying indeed. A horrifying idea right there. So, ooh, maybe I'll sing tonight. What do you think? What do you think? Maybe I'll do a little bit of reading and then I'll sing. Because it's been a little boring, hasn't it? Hasn't it? Which songs shall I sing? Anybody? Any request? I wouldn't yell at my... Hello, normal guy. Chance? What does that even mean? What does that mean? OnlyFans chance. What does that mean? Do you even understand English? Can you string together a sentence, or is that too difficult for you? Oh, Nathan, don't even worry about it. Just relax. Try to sleep with the cosmology in the background. There is some people here. Oh, Doro, really? Aw, I think I hurt his feelings. Aw. Oh, normal guy. Mommy loves you. Your real mother, I mean. No need to be so sad. Mommy and Daddy love you. Okay? Oh, Dora only timed you out for 300 seconds. I know you can do a lot in that time. This picture of a universe, I'm going to start talking about the universe again, that started off very hot and cooled as it expanded is in agreement with all the observational evidence that we have today. Nevertheless, it leaves a number of important questions unanswered. Why was the early universe so hot? Why? Why is the universe so uniform on a large scale? So uniform, more or less the same-ish on a large scale. Now, there are certain areas of overdensities, remember. This is how and why we have galaxies and stars. But for the most part, the universe is rather uniform, isotropic. I heard we were singing tonight. We may. Do you have a song request? You might want to be a bit more productive and request a song if you need some singing. So, why does it look about the same at all points of space and in all directions? So, it's more or less homogeneous and more or less isotropic. Other than little areas of overdensities, which is, of course, the stars and galaxies. But remember, that's not most of the universe. Most of the universe is kind of like homogeneous, isotropic. In particular, why is the temperature of the microwave background radiation so nearly the same when we look in different directions? This is what people really mean when they talk about the smooth universe, the early universe, the smooth universe. When we took a measurement of that cosmic microwave background radiation, remember, many times, it was studied for a number of years. I think something like 20 years at least it was studied, the CMB. And people tried to measure it in all these different directions, and it comes out to be the same temperature, no matter in what direction you kind of try to measure it. I heard you were a big Taylor Swift fan. Yes, indeed. I have been to her concert at Ohio State University in the year 2018 when she came, and that was the only time I was in that football stadium, and her production was the biggest production of that stadium ever. Ohio Stadium, even though the stadium is, of course, known for football, which I have never been to a game at Ohio State, even though I did go there as grad school. But I did go into the stadium only to hear Taylor Swift live. And actually, let me just take a pause here. I had like I had probably a couple drinks in my hand, like I don't know exactly what they were. And I had two friends with me, and I was like, you hold this, you hold this. And they were both guys, actually. They were two friends. I was like, you hold this, you hold this. And I was like, ah, like screaming as she entered the stage. So that's my Taylor Swift concert story. I'm a big fan of powerful women who carve out their own space in history and space and time. Yeah, so Ohio Stadium, so she had a massive production. She had 52 semi-trucks parked in our parking lots. Okay, I was basically not going to go because I was going to graduate and like defend my thesis. So I was very, very busy and overwhelmed. But then I kept seeing her semi-trucks full of, I'm guessing full of stuff. I didn't look inside. But her trucks were just parked everywhere at all these parking lots, right? Because ahead of the show. And I was like, I kept seeing them. And I'm like, oh my gosh, I have to. And then I just like bit the bullet. And I'm like, okay, I'm going to get 3 tickets for me and 2 of these friends. And those 2 men who went with me were the only men or felt like it in the whole stadium. So yes, you're right. Army of young ladies is correct. And we all screamed a lot. It was amazing. It was the most amazing show. She had basically like a music, sound, and light show and everything. It was probably Reputation. That was probably the show. I think it was her Reputation album. It was so good. I went with these 2 friends, and they're like, they were happy too. And I got their tickets. Like, I bought the ticket for all 3 of us. And I'm like, you're going, we're going. And they were just happy to hold my drinks as I screamed like my head off when she came in, and she like did her songs and dancing and everything. So yeah, yes. What was that song again that I tried to sing one time? Listen for the best. My reputation's never been worse, so you must like me for me. Dang. Okay, you know what? Later. We will sing more later. At this point, I'm busy. So why is the temperature of the cosmic microwave background radiation more or less the same in every direction? This is the question. It is a bit like asking a number of students an exam question. If they all give exactly the same answer, you can be pretty sure they have communicated with each other. Yet, in the model described above, there would not have been time since the Big Bang for light to get from one distant region to another. So it's not like it's not like the different parts of the universe are communicating with each other necessarily since the Big Bang, because light can't travel that fast from one, different corner to another different corner of the universe. And so it's almost like, how did this information travel? It's almost like, how did the entire universe know to be so smooth? How did the cosmic microwave background end up being so smooth and about the same temperature everywhere, no matter what direction you're looking? And that's really sort of this mystery. So if they all give, it's like asking a number of students a question on an exam. If they all give exactly the same answer, you can be pretty sure they have communicated with each other. Yet, in the model described above, there would not have been time since the Big Bang for light to get from one distant region to another, even though the regions were close together in the early universe. But after the universe expanded and became bigger, that is, light would not have had time to get from one distant region to another. According to the theory of relativity, if light cannot get from one region to another, no other information can. So again, according to general theory of relativity, according to relativity period, both special and general, nothing is going to travel faster than light. So if light cannot travel from one region of the universe to another, that means no information can really pass through that distance. And so how come we are getting the same temperature for the CMB, or the cosmic microwave background radiation, no matter which direction we look in and how we do the measurement, in what direction we do the measurement, and that too over years? So this was kind of confirmed over the years that this was the case. Hello. Government money? What does that mean? Combat sports, hello. She's singing tonight. I like money, as you should. Doro, you know that. Her songs are my weakness. Oh my gosh, combat sports. Combat sports is actually good at requesting songs. Combat sports, can you request some songs? Because these other guys are not being very requesting. They don't know what to request, but I think combat sports actually knows a number of Bollywood songs. So you should request something and give me an idea what to sing, and I will sing that. I don't know why Taylor Swift took the government money. She didn't have to sell out. I don't know what you mean by that. I don't know about that. Government money for what? I thought she just made a bunch of money, period. I don't know why she would need. When he says Taylor... Oh! When it was proven she took money from the Democratic Party to represent Kamala? Isn't that like more recent? I'm talking about watching her concert in 2018. Oh, you mean like she gave advertising for Kamala Harris and like charged for that? I mean, I guess she is a brand, like she has a lot of brand value. So maybe she charges to represent or advertise for politicians. I don't know. I don't know these things. Kal ho na ho. Okay. Okay. We're going to sing Kal ho na ho. Okay. I see. Oh, I didn't know about that. Sell out all day? I'm not a fan anyway. Of what? Music, her, or the money? It's kind of like, yeah, I guess she charges. Maybe she charges for, advertising. Oh, Taylor Swift. We love Taylor Swift. Okay. If they all give exactly the same answer, yet in the model described above, they would not have had time since the Big Bang for light to get from one distant region to another. According to the theory of relativity, if light cannot get from one region to another, no other information can. So there would be no way in which different regions in the early universe could have come to the same temperature as each other unless for some unexplained reason they happen to start out with the same temperature. Why did the universe start out with so nearly the critical rate of expansion? So that's the next question. Combat sports does actually request some very good songs, and I'm absolutely gonna sing Kalihonaho. It's one of my favorite movies that I grew up with. So combat sports also like basically request songs from movies that I grew up with. So that's good as well, because if you ask me something that's super recent and I haven't seen it or watched it, nor do I know the song, then that would be hard. But combat sports is extremely good at knowing the songs, maybe because we are I'm getting a notification, whatever. Maybe it's because we're peers or close age. You guys, or he knows the same songs, which is excellent. Why did the universe start out with so nearly the critical rate of expansion? That's the other next question that separates models that recollapse from those that go on expanding forever. That even now, 10,000 million years later, it is still expanding at nearly the critical rate. So expanding at nearly the critical rate, that's the other mystery. Because here's the clincher. Like listen to the sort of, there's consequences for this rate of expansion. And if the rate of expansion was something else, the universe could have been quite different. If the rate of expansion 1 second after the Big Bang had been smaller by even 1 part in 100,000 million, the universe would have recollapsed before it ever reached its present size. So remember we talked about the rate of expansion, how you can have a rate of expansion that is small enough where the universe basically recollapses. You can have a rate of expansion that is just enough to avoid the recollapse, or you can have a rate of expansion that is quite high and basically you avoid recollapsing always. Like you can never really recollapse. So we actually looked at a graph for this a while ago, and this is kind of what's coming up again. And this expansion of being at the critical rate is quite interesting, despite the fact that the universe is so universe. So question number 4, despite the fact that the universe is so uniform and homogeneous on a large scale, it also contains those local irregularities or those local little overdensities that I was mentioning a little while ago, which is of course the stars and galaxies. Without the overdensities, without those sort of clumps of matter here and there, of course we would not have galaxies and stars and us and things like that. So even though the universe is largely, as in on a large scale, very homogeneous, very isotropic, as in homogeneous, about the same everywhere. Isotropic means no matter which direction you look in, it's basically the same-ish. There's still, on a smaller scale, on a local-ish scale, of course, there's those irregularities. Can ours recollapse? That's a great question. We will get into it. These are thoughts to have developed from small difference. These are thoughts. So the local irregularities, such as stars and galaxies, are thought to have developed from small differences in the density of the early universe from one region to another. What was the origin of these density fluctuations? So the fact that at a local scale, there are fluctuations in the density, these fluctuations, basically fluctuations meaning over densities, having a little over density somewhere is sort of this fluctuation of the density, right? Very tiny fluctuations, because remember we mentioned the smooth universe a lot when we talked about cosmology, and that's basically overall, for the most part, the universe is smooth. It's really a higher order effect that there are these little fluctuations in the density. Sometimes they're called higher order high order perturbations. So higher order perturbations of the smooth universe. That's actually the sort of this topic formally. And those have led to the galaxies and the stars. But we have to probe and try to understand why there are even those fluctuations. Why are there these higher order perturbations? So this is a very important question in cosmology because, of course, it leads to large scale structure, galaxies, stars, and there is a belief that dark matter actually has some role in this. So we'll try to figure it out. We will see what these people say about this topic and probe this, but that's kind of what the overall feel of it. So as far as can ours recollapse, so basically we are expanding at the critical rate where we should avoid a recollapse. But also we're not, so if we expanded at a rate smaller than the critical rate, then we would have recollapsed by now. It would not have gotten to the present size. The universe has gotten a lot bigger than it used to be, and we would not have gotten to this size if it recollapsed earlier, obviously, right? But we're expanding at exactly the critical rate, which is a very interesting phenomena, because we could also have been expanding at much faster rate. And so, and by the way, I would take this exact rate of expansion. We talked about this a lot during our cosmology specific lives, where we were consulting with the reference book by Scott Dodelson. And remember that to figure out this rate of expansion, you have to basically fit your cosmology model to what you're seeing in observation, and then kind of understand the rate. So measuring the rate is not so trivial, right? So take it with a little bit of a grain of salt, because ultimately they do fit the model to the data and figure out the critical rate of expansion from there. But basically there is definitely some possible numbers, right? If you expand too fast, then you're never going to recollapse. If you expand too slow, then you could recollapse. And it seems like we're in the ballpark of where we will not recollapse. And that too is a bit of a mystery as to why that is. Why are we expanding at a rate that is sort of the critical rate or in the ballpark? I don't know how much it's exact. I have to, learn more about that. But as far as the ballpark of where we are not supposed to be recollapsing. Or basically, if this critical rate was not the case, then we would have recollapsed by now. The universe is very big already. We wouldn't have made it to this current size if the recollapse was going to happen. Thank you so much for the hearts. Can we get 10 likes? Can we get 20 likes? That would be amazing. The general theory of relativity on its own cannot explain these features or answer these questions because of its prediction that the universe started off with infinite density at the Big Bang singularity. So you can't just rely on general theory of relativity to answer all these different questions. These are some very important questions. Cosmology kind of stands on general theory of relativity and this expanding universe from the Big Bang singularity and all that stuff. But at the same time, remember that cosmology as a field has really started to evolve in the last 100 years or so. It's actually a kind of more recent field. We didn't even know that there were so many more galaxies beyond our own galaxy until 100 years ago, when Hubble did his thing, his observations telling us that there were a lot more galaxies, and we didn't really understand the size of our universe and the scale of our universe until more recently. And cosmology really has to do with the study of that universe, the study of the entire universe and how it expanded from the Big Bang, and the fact that it's expanding, why is it expanding? The concept of dark energy, which we think is making it expand, those types of things. And this large scale structure question, why did we even have overdensities in some spots to make the stars and galaxies, right? Those types of questions, when answered at the scale of the universe, is cosmology, which is a relatively young field. It's more young than, for example, astronomy. Astronomy has been around forever, traditionally done with visible light, of course, by looking at the stars in the sky, the stars in the sky. I mean, most things, most objects in the sky are probably, galaxies or binaries and things like that too. So, but we say stars, right? But so basically, like doing, looking at the sky and looking at the heavenly bodies and trying to understand them, or observing them. That's astronomy. It's been around forever. But cosmology as a field is not as new. It's about 100 years old. So some of these facts really have more detail that you have to really pay attention to. So just keep that in mind as we keep going forward, okay? So the general theory of relativity on its own cannot explain these features or answer these questions because of its prediction that the universe started off with infinite density at the Big Bang singularity. At the singularity, general relativity and all other physical laws would break down. So because that's the thing, a singularity is sort of this mathematical concept where you have a point of infinite density. We actually saw that this is also the case with black holes. It's also a singularity. But it's sort of this thing that general relativity doesn't like, basically. As explained before, this means that one might as well cut the Big Bang and any events before it out of the theory because they can have no effect on what we observe. Space-time would have a boundary, a beginning at the Big Bang. So this whole question of, like, space-time and how it acts, how it is affected by gravitation. It's, the massive bodies that bend space-time. All of that is general theory of relativity, right? But in the beginning, when the universe started with the Big Bang, and it's that infinite density singularity thing, that's not really explained by general theory of relativity. It's what makes sense. It's where we come from, but it's not really an explanation. You know what I mean? Hello, righteous monk. তুমি এত রূপবতী যে কিছুই বুঝতে পারছি না. Hello, righteous monk. Good to see you here. Please do like and share and subscribe. So, space-time would have a boundary, a beginning at the Big Bang. Science seems to have uncovered a set of laws that, within the limits set by the uncertainty principle, tell us how the universe will develop with time, if we know its state at any one time. These laws may have originally been decreed by God, but it appears that he has since left the universe to evolve according to them and does not now intervene in it. So even if God is who is responsible for the beginning or before the beginning of the universe with the Big Bang, it seems that now we kind of evolve without God's intervention, according to Stephen Hawking here, because universe is doing its thing, the dark energy or whatever it is that makes us expand, it's doing its thing, and it's doing it at the critical rate. So it's interesting, and we still are in the process of understanding what really is happening in cosmology. So these laws may have originally been decreed by God, but it appears that he has since left the chat to evolve according to them and does not now intervene in it. But how did he choose the initial state or configuration of the universe? What were the boundary conditions at the beginning of time? So this is another thing in physics that we see a lot. We want to see what the boundary conditions are. Where do things kind of break down? Where do things, what's the edge of the problem, if you will? And in this case, we of course have an edge. It's the beginning of time. It is when the universe got started with the Big Bang. So indeed, that if there is an edge, that's what it is, and we would want to sort of understand the conditions of that edge. So one possible answer is to say that God chose the initial configuration of the universe for reasons that we cannot hope to understand. This would certainly have been within the power of an omnipotent being, but if he had started it off in such an incomprehensible way, why did he choose to let it evolve according to laws that we could understand? So we could say that the laws of physics, we're able to comprehend, we're able to study it, we can understand it. But how come we can understand these things but not the beginning of the universe, or the very, very beginning, or just before the beginning, if there was a before, right? That's sort of our question. And actually, this is sort of a topic that is debated between atheists and religious folks. I've actually been to a debate between Dr. Lawrence Krauss, and someone else. I forget the someone else, but they were basically debating about the existence of God. Now, I don't want to get into this debate right now here, but it does exist. These debates do happen, especially between cosmologists and religious people, because cosmologists are talking about the beginning of the universe, the early universe, and whether what role is there in it of just nature and the universe doing its thing according to laws that we understand, and what role is there of a higher being. So this is the sort of thing that can kind of come up if you ever were to go to that type of debate or topic. This class session is deep. I know. Tell me about it. This would certainly have been within the power of an omnipotent being, but if he had started it off in such an incomprehensible way, why did he choose to let it evolve according to laws that we could understand? The whole history of science has been the gradual realization that events do not happen in an arbitrary manner, but that they reflect a certain underlying order, which may or may not be divinely inspired. It would be only natural to suppose that this order should apply not only to the laws, but also to the conditions at the boundary of space-time that specify the initial state of the universe. Because it could also be the case that we are just dumb and don't understand the initial state of the universe all that well yet, and simply are in the process of doing that research. So that could also be the case. And I'm not saying dumb in a bad way. Maybe we haven't learned everything there is to learn to understand the beginning of the universe. Hello, Batman. Hello, Faze. Hello, everybody. Kubi kotin bishoy amar matha ghurche bapre. I'm in love. Hello. Somebody is here is writing in Bengali, which I can read quite well. So thank you so much for the Bengali comments. Thank you, thank you, thank you. So it would be only natural to suppose that this order should apply not only to the laws, but also the conditions at the boundary of the space-time, which is the beginning of time. There may be a large number of models of the universe with different initial conditions that all obey the laws. There ought to be some principle that picks out one initial state and hence one model to represent our universe. One such possibility is what are called chaotic boundary conditions. So are you ready for the chaos? Chaotic boundary conditions. These implicitly assume either that the universe is spatially infinite or that there are infinitely many universes. Under chaotic boundary conditions, the probability of finding any particular region of space in any given configurations just after the Big Bang is the same, in some sense, as the probability of finding it in any other configuration. The initial state of the universe is chosen purely randomly. This would mean that the early universe would have probably been very chaotic and irregular, because there are many more chaotic and disordered configurations for the universe than there are smooth and ordered ones. If each configuration is equally probable, it is likely that the universe started out in a chaotic and disordered state simply because there are so many more of them. See, I'm not sure that I am a big fan of the whole multiverse thing, but I'll entertain it. It is difficult to see how such chaotic initial conditions could have given rise to a universe that is so smooth and regular on a large scale as ours is today. So how did the chaos lead to something so elegant, so smooth, so isotropic, so homogeneous? So that's sort of a question as well. One would also have expected the density fluctuations in such a model to have led to the formation of many more primordial black holes than the upper limit that has been set by observations of the gamma ray background. So remember, Stephen Hawking of course, worked on black holes on his thesis. He gave us Hawking radiation, that the fact that there could be quantum fluctuations leading to some emission from black holes, even though from classical physics like general relativity, we of course thought that there can be nothing that escapes a black hole. So that's sort of the background here, but he actually predicted primordial black holes, or maybe wished for them to exist. And then, we looked for them in observation, for example, the gamma ray bursts and all that, to see if maybe primordial black holes could be an explanation for them. But from those observations, we were able to set a limit based on not finding primordial black holes. And so he's, kind of being like, okay, well, if there was so much chaos, then why didn't we have more primordial black holes? As somebody who may be a little biased towards primordial black holes, Stephen Hawking. So one would also have expected the density fluctuations in such a model to have led to the formation of many more primordial black holes than the upper limit that has been set by observations of the gamma ray background. If the universe is indeed spatially infinite, or if there are infinitely many universes, there would probably be some large regions somewhere that started out in a smooth and uniform manner. Yay! It is a bit like the well-known horde of monkeys hammering away on typewriters. Most of what they write will be garbage, but very occasionally, by pure chance, they will type out one of Shakespeare's sonnets. So if you had a lot of universes, a lot, then that also increases the chance of this Shakespeare thing happening with the monkeys. Similarly, in the case of the universe, could it be that we're living in a region that just happens by chance to be smooth and uniform? At first sight, this might seem very improbable because such smooth regions would be heavily outnumbered by chaotic and irregular regions. However, suppose that only the smooth regions were galaxies and stars formed and were conditions right for the development of complicated self-replicating organisms like ourselves, who were capable of asking the question, why is the universe so smooth? This is an example of the application of what is known as the anthropic principle, anthropogenic meaning human stuff. So I'm guessing anthropic is something to do with people. Anthropic principle, which can be paraphrased as we see the universe the way it is because we exist. We see the universe the way it is because we exist. Oh my gosh. Gosh, oh gosh. We see the universe the way it is because we exist. Ah! There are two versions of the anthropic principle, the weak and the strong. The weak anthropic principle states that in a universe that is large or infinite in space and or time, the conditions necessary for the development of intelligent life will be met only in certain regions that are limited in space and time. The intelligent beings in these regions should therefore not be surprised if they observe that their locality in the universe satisfies the conditions that are necessary for their existence. Maybe I should learn more about this anthropic principle. Maybe it's a thing in philosophy or something that I just didn't know about. It's a bit like a rich person living in a wealthy neighborhood, not seeing any poverty. So it's almost like, are we seeing a smooth and awesome and isotropic universe because we're like that rich person who lives in a rich neighborhood and does not see any poverty of, I guess, more chaotic, ugly universes? One example of the use of the weak anthropic principle is to explain why the Big Bang occurred about 10,000 million years ago. It takes about that long for intelligent beings to evolve. As explained above, an early generation of stars first had to form. These stars converted some of the original hydrogen and helium into elements like carbon and oxygen, out of which we are made. Remember? We're made out of carbon and oxygen and things like that. The stars then exploded as supernovas, and their debris went to form other stars and planets, among them those of our solar system, which is about 5,000 million. So, I mean, we're about 5 billion years old. He keeps saying the 1,000 million. You know, 1,000 million is a billion, right? So it's a little silly to say 1,000 million all the time, but whatever. The first 1 or 2,000, 1,000 million, billion years of the Earth's existence were too hot for the development of anything complicated. The remaining 3,000 million years or so have been taken up by the slow process of biological evolution, which has led from the simplest organisms to beings who are capable of measuring time back to the Big Bang. So it's almost like maybe we needed to be here, us intelligent beings, so intelligent, who can actually study the evolution of the universe, to then ask the question about the why the universe is the way it is. It's because we exist, and I don't know. Few people would quarrel with the validity or utility of the weak anthropic principle. Some, however, go much further and propose a strong version of the principle. According to this theory, there are either many different universes or many different regions of a single universe, each with its own initial configuration and perhaps with its own set of laws of science. In most of these universes, the conditions would not be right for the development of complicated organisms. Only in a few universes that are like ours would intelligent beings develop and ask the question, why is the universe the way we see it? The answer is then simple. If it had been different, we would not be here. Righteous says, saying beautiful hair. The laws of science, as we know them at present, contain many fundamental numbers, like the size of the electric charge of the electron and the ratio of the masses of the proton and the electron. We cannot at the moment. Remember, we were talking about Brian Greene's Elegant Universe. We were talking about the fine balance of the universe. Remember about that? This is sort of in the same vein. There's a lot of little things, quite literally sometimes, that are in a fine balance in this universe. Maybe we just live in a really beautiful, elegant one, and we are supported by that same universe, the beautiful, elegant universe, who can create intelligent beings enough to then ask about the beauty of this universe. But there is a number of very sort of magical, miraculous, fine balanced numbers and things going on in the universe as well. So we cannot at the moment at least predict the values of these numbers from theory. We have to find them by observation. It may be that one day we shall discover a complete unified theory that predicts them all, but it is also possible that some or all of them vary from universe to universe or within a single universe. See, remember, we talked about how we keep finding these particles in particle physics with all these different numbers for their mass, charge, etc. And it's like, is this random, or are we just kind of collecting upon, are we seeing a snapshot of this that is like this here in this universe, and in a different universe, maybe they have a different number? You know, maybe the mass of the electron in a different universe is different. Isn't that crazy? Ah! Oh my gosh. And maybe that universe didn't make it. And we made it. Because, I mean, if the mass of the electron was, remember how if the mass was of the electron was bigger, we might have been in, actually, let me think about that. If the mass of the electron had been bigger, let me think about that. I think I remember how the fine balance of the electromagnetic force, the weak nuclear force, and the strong force were all sort of on a fine balanced situation. I bet, I mean, you know what? Now I'm liking the multiverse theory more, because there might be universes where things just died, you know? There might be a universe where the mass of these particles or the charge or the something is different. Oh! And then those universes didn't make it. Maybe they didn't evolve like ours. Aw, poor things. The remarkable fact. Okay, so we have to find them by observation. These numbers, for example, the numbers I kind of talked about right now. It may be that one day we shall discover a complete unified theory that predicts them all. Maybe that's why the unified theory is so difficult, because you kind of have to almost explain other universes too, potentially. Ah. Oh, wasn't there something about dark matter being like, other universes getting, oh no, oh my gosh. Maybe other universes can explain dark matter. Oh, you know what I mean? Maybe other universe, like dark matter could be sort of like other universes coming and going in and out of existence, maybe. And that could be why we have dark matter. I don't know. Okay, we'll see. I don't know. We'll see what he says. I'm sure he's going to say something about that. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. So So that's the fine balance, more of the fine balance situation that we're talking about, is that the fine tuning, as you said, to make us happen is sort of remarkable. For example, if the electric charge, this is it. So it might not be the mass, but it might be the electric charge. The mass could be important too. Like the mass of the electron in a different universe could literally be different, but the electric charge, I think, is an interesting one. So for example, if the electric charge of the electron had only been slightly different, stars either would have been unable to burn hydrogen and helium, or else they would not have exploded. Of course, there might be other forms of intelligent life not dreamed of even by writers of science fiction that did not require the light of a star like the sun or the heavier chemical elements that are made in stars and are flung back into space when the stars explode. Nevertheless, it seems clear that there are relatively few ranges of values for the numbers that would allow the development of any form of intelligent life. Most sets of values would give rise to universes that, although they might be very beautiful, would contain no one able to wonder at that beauty. One can take this either as evidence of a divine purpose in creation and the choice of the laws of science, or as support for the strong anthropic principle. অনেক জটিল বিষয়. Have fun, righteous. Now I'm choking. There are a number of objections that one can raise to the strong anthropic principle as an explanation of the observed state of the universe. First, in what sense can all these different universes be said to exist? I think we were talking about this the other day. I want to remind myself, but I think if the charge of the electron had been bigger, then the electromagnetic force between protons in the nucleus and electrons would have been bigger, and maybe that would have interrupted nuclear processes that make, for example, hydrogen to helium, helium to carbon, and higher. So maybe that's what it is. Carbon has 6 protons and 6 neutrons, right? So you need so carbon is 12, right? 6 plus 6. So you need 4 helium nuclei, for example, to make carbon, right? So these are nuclear processes. The nuclei of different elements have to want to combine. There has to be enough energy, of course, but also they need to combine. But if the electromagnetic force was too high between the electron and the proton, then that could have maybe overtaken the process. I think that there was something like that, which this is why we get heavier nuclei. And if we didn't have heavier nuclei, then we wouldn't be here, right? Because the Big Bang made hydrogen and a little bit of helium, but it's really the overdensities that formed in the universe, which then gave us galaxies and stars. The stars combine helium to give us heavier elements, such as carbon, oxygen, etc. Every element heavier than helium pretty much has to be made in stars. So the nuclear processes in stars give us those heavier elements, and then when the stars die and explode, that material is spewed into the interstellar medium, which can form gas clouds and stuff like that, and those can condensate and make the next generation of stars and sometimes planets like we came to be. So it's really that process. But that process of stars and galaxies and whatnot, really what's going on is the nuclear process, right? It's the nuclear reactions that make those heavier elements that then lead to us being made of carbon, oxygen, etc. So life forms need those heavier elements. You can't make too much life form with just hydrogen, which is what the universe mainly has. Our universe, mainly abundantly, most abundant element is still hydrogen, because that's what we got from the Big Bang. So yeah, this fine balance between the electric charge and the electromagnetic force winning sometimes, but not winning so much, where we then also can have strong nuclear force be a thing, is very important to our existence. We have to thank the strong nuclear force, okay? Okay, so we'll keep going for a bit. There are a number of objections that one can raise to the strong anthropic principle as an explanation of the observed state of the universe. First, in what sense can all these different universes be said to exist? Let me put my feet up on the media cabinet. That would be helpful. There, can you see me? Hopefully you can. We should first, in what sense can all these different universes be said to exist? If they are really separate from each other, what happens in another universe can have no observable consequences in our own universe. We should therefore use the principle of economy and cut them out of the theory. If, on the other hand, they are just different regions of a single universe, the laws of science would have to be the same in each region, because otherwise one could not move continuously from one region to another. In this case, the only difference between the regions would be their initial configurations, and so the strong anthropic principle would reduce to the weak one. A second objection to the strong anthropic principle is that it runs against the tide of the whole history of science. We have developed from the geocentric cosmologies of Ptolemy and his forebears through the heliocentric cosmology of Copernicus and Galileo. Hello, Ram Candy. Hi, Ram Candy. How are you? Can you see me okay? To the modern picture in which the Earth is a medium-sized planet orbiting around an average star in the outer suburbs of an ordinary spiral galaxy. So we are in an outer suburb, as you might know, which is itself only one of about a million galaxies in the observable universe. Yet the strong anthropic principle would claim that this whole vast construction exists simply for our sake. This is very hard to believe. Our solar system is certainly a prerequisite for our existence, and one might extend this to the whole of our galaxy to allow for an earlier generation of stars that created the heavier elements, but there does not seem to be any need for all those other galaxies, nor for the universe to be so uniform and similar in every direction on the large scale. Oh no, hopefully you're okay, Ram Candy. So this whole strong anthropic principle doesn't hold much water in the sense of we are not that special. We're, on a medium planet at sort of a medium distance from the sun, which is an average star in the outer suburbs of an, I guess, average spiral galaxy. Although I do think that our galaxy is quite beautiful, has a beautiful shape, and lots of really nice features. I was going to say things and features, thingsters. But I guess we're not that special. It doesn't really explain why do all those other galaxies exist if we're so special. You know, one would feel happier about the anthropic principle, at least in its weak version, if one could show that quite a number of different initial configurations for the universe would have evolved to produce a universe like the one we observe. If this is the case, a universe that developed from some sort of random initial conditions should contain a number of regions that are smooth and uniform and are suitable for the evolution of intelligent life. On the other hand, if the initial state of the universe had to be chosen extremely carefully to lead to something like what we see around us, the universe would be unlikely to contain any region in which life would appear. It's almost like the universe is there's so much redundancy. It's almost like if we're the whole point of this, then why are there so many extra galaxies and whatnot? You know, that's that's sort of a question here. Thank you for liking the live. I have to go in a bit, but it's a it's indeed a question about these other galaxies and the fact that we have to have a certain type of prerequisite before we can really support life form, which seems to be our type of solar system, you know? Thank you for being here. Thank you, Ram Candy. Thank you, everybody. We'll keep going for a bit. On the other hand, if the initial state of the universe had to be chosen extremely carefully to lead to something like what we see around us, the universe would be unlikely to contain any region in which life would appear. In the hot Big Bang model described above, there was not enough time in the early universe for heat to have flowed from one region to another. This means that the initial state of the universe would have to have had exactly the same temperature everywhere in order to account for the fact that the microwave background has the same temperature in every direction we look. The initial rate of expansion also would have had to be chosen very precisely for the rate of expansion still to be so close to the critical rate needed to avoid recollapse. This means that the initial state of the universe must have been very carefully chosen indeed if the hot Big Bang model was correct right back to the beginning of time. It would be very difficult to explain why the universe should have begun in just this way, except as the act of a God who intended to create beings like us. In an attempt to find a model of the universe in which many different initial configurations could have evolved to something like the present universe, a scientist at the Massachusetts Institute of Technology, Alan Guth, suggested that the early universe might have gone through a period of very rapid expansion. This expansion is said to be inflationary, sort of like inflation in economy, right? Meaning that the universe at one time expanded at an increasing rate rather than the decreasing rate that it does today. According to Guth, the radius of the universe increased by a million, one with 30 zeros after it, times in only a tiny fraction of a second. Guth suggested that the universe started out from the Big Bang in a very hot but rather chaotic state. These high temperatures would have meant that the particles in the universe would be moving very fast and would have high energies. As we discussed earlier, one would expect that at such high temperatures, the strong and weak nuclear forces and the electromagnetic force would all be unified into a single force. As the universe expanded, it would cool and particle energies would go down. Eventually, there would be what is called a phase transition, and the symmetry between the forces would be broken. The strong force would become different from the weak and electromagnetic forces. One common example of a phase transition is the freezing of water when you cool it down. Liquid water is symmetrical, the same at every point and in every direction. However, when ice crystals form, they will have definite positions and will be lined up in some direction. This breaks water's symmetry. So there is this symmetry breaking type of explanation of why the four types of forces kind of separated out and became these four types of forces. They might have been part of the same thing, but maybe there was sort of a phase transition in the universe where now we have these four types of forces. So there's a little bit more in this chapter, Origin and Fate of the Universe. We will continue this tomorrow. Let's see. Gotta run, but it's been most excellent. Thank you so much for being here. Thank you, thank you, thank you. Thank you, thank you, thank you. Good night. Have a great night. See you tomorrow. I think it'll be tomorrow afternoon if I'm able to go live tomorrow. And see you so very soon. Have a good night. Thank you, Doro. Thank you, Ram Candy. Thank you, everybody. Thank you so much for your likes, shares, subscribes, comments, as usual. Much appreciate all of the support. Please do check out our videos, shorts, lives, and everything. The live uploads show up under the live tab on the channel. So please do keep on keeping on, keep on supporting. Really appreciate it. Enjoy. Have a great night. Thank you. Bye.